Today I'm going to talk a little bit about corralling big data at TACC and some of the deployment we're working on. In fact, that was alluded to in Jeff's talk. So just a little bit about TACC. We're the Texas Advanced Computing Center. Our mission really is to enable scientific discoveries and enhance society through the application of advanced computing technologies. And we kind of accomplish this in two different areas. Number one is we deploy resources and services. So of course we want to deploy the latest technology, evaluate and acquire the most advanced computing systems, and provide training, consulting, and for all of our users on how to use those systems, but also provide our own research and development activities that complement those resources and services. So we collaborate with researchers to take best advantage of our latest technologies and also conduct our own research, whether it's on Lustre, MPI, or running large-scale systems at TACC. So I broke down kind of our storage needs into three different areas. So we always want to have some cluster-specific storage. And typically this is the highest performance storage. It's usually called our scratch file system. But we're talking about tens to hundreds of gigabytes a second bandwidth, very large capacity. Right now we're in between somewhere between 2 to 5 terabytes per teraflop. Unfortunately, we have to purge these file systems frequently, though. So it's something just that we have to live with on these big, large scratch file systems. And of course, we want it very scalable. So we need to support thousands of clients on these file systems. At the other end of the architecture, we have the permanent archival storage, and this is the tape library. And really, this is maximum capacity, many petabytes, but it's usually slow performance. And in the case of us, we actually do use tape-based technology still, but with a spinning cache storage. In between that is kind of this center-wide persistent storage, and this is something that our users have requested over the years. But really what they want is they want an easily accessible place where they can access their data from lots of different systems. We run multiple systems at TACC, and they want to be able to get access to their data wherever they're working. So for this, we need to make it available. It needs to be large capacity. We need to be able to enforce quotas. We set up these file systems such that we have quotas enabled on them, and that way we can make sure that no one user is hogging up more of the file system than they should have access to. And typically this has been moderate performance, but key here is that we want it very reliable and highly available. We realize the clusters are sometimes going to have system maintenance, but we want to make sure that we have as much uptime on this center-wide persistent storage as possible. So we've been working with DDN for several years at TACC. Our very first deployment was late 2005 with a system that went into production in 2006 called Lone Star 3. These were using the S2A technology. We were very happy with it. We had 3 controllers at the time, 120 terabytes of storage, and on the order of about 10 to 20 gigabytes a second actually about 10 gigabytes a second of max performance on that file system. To meet the need of the global persistent storage, we actually deployed Corral. Corral is limited to UT system users only, so it's not available to our national users because it was funded through project funds that were provided by UT system. And this was using the DDN S2A 9900 controller and about 1.2 petabyte of disk. In 2010, we deployed Lone Star 4, which is the follow-on to Lone Star 3, upgraded to the latest DDN SFA 10,000 controllers, and added about 1.8 petabytes of disk to that system. In 2011, we did a similar upgrade to Corral. Corral was upgraded with DDN SFA 10,000 controllers and about 5 petabytes of disk. One comment on these file systems, we typically have run Lustre on most of these file systems. However, the most recent Corral upgrade, we actually switched over to using GPFS provided by DDN. And the main reason for this was actually we've replicated this exact hardware. It's designed for disaster recovery purposes in that we have another 5 petabytes identical located at a data center up in Dallas at another UT system institution, UT Arlington. And we use GPFS to control the replication of the data between the sites. So based on what we learned with Corral, we really wanted to deploy a global file system. So we've had lots of user requests for persistent storage. We realized, they realized that we could put them onto the tape library, but inevitably that means they're going to have to recall the data off the tape and get it back so that they can use it on the storage. So what we wanted to be able to do is provide enough capacity so that they could get their research and their data needs met without having to worry about being purged or removed from the scratch file system, and keep it persistent. And of course, I mentioned Corral was limited to UT system users only, and we have thousands of other users that come across from other institutions funded by National Science Foundation on our systems. So we wanted to be able to support those users with a global file system. So we issued an RFP earlier this year, and basically we set just a couple of requirements. We really wanted a large capacity file system. So we required at least 20 petabytes of usable storage on this file system. We realized that we really didn't need the ultimate performance, but we did need something that was at least going to give us a pretty good amount of aggregate bandwidth. So we selected at least 100 gigabytes a second of aggregate bandwidth. And the key focus, of course, is the high availability and reliability. We want to make sure that we can access the file system, meet a very high uptime requirements, and make sure that the data is always available for our users, whichever system they happen to be running on at TACC. And of course, we got several bids from multiple vendors, and in this case, we ended up selecting a DDN solution for the project. They offered the best capabilities, met all the requirements that we met, and actually had some of the best pricing for the storage. So I just have a picture of the file system actually in deployment. I do want to point out this is actually Ariel Martinez. Some of you may recognize him as a DDN engineer. He's been on site helping us deploy the hardware. But this is actually when we had 4 of the 50 U-racks in the front here, and they were just populating all the drives and putting them all in. And we actually had space where we're going to put the storage servers for the file system. So basically the design that we selected on this is we wanted a Lustre 241 based global file system. And we wanted to have scalability for future upgrades. We want to make sure that we can keep up with the latest technologies, potentially replace controllers, drives, or even expand the storage should additional funding become available through some of our other partners. So we built it upon a scalable unit design. Each scalable unit has 16 object storage servers, providing access to 168 OSTs of RAID 6 arrays. Each one of these scalable units has 2 SFA 12K couplets and has about 5 petabytes of usable capacity and 25 gigabytes a second of throughput per scalable unit. We deployed 4 of these scalable units that provides up to the 20 petabytes and actually has capability to go beyond 100 gigabytes a second should we add additional spindles. Now, to make it available through all the other systems and still maintain high availability, we actually are using the Lustre LNet routers for external mounts. We didn't want to connect the file system up to any of our existing InfiniBand file systems or clusters, and so that in case we had downtime on the cluster, we didn't want to have to take downtime on the file system. We codenamed this project Stockyard, very similar to Corral and Ranch, complements some of our other themes for storage at TACC. And one bit I didn't mention on here, but I should just point out the metadata servers are using the SFA 7700 controller, or 7700 storage unit for all the metadata activities. Just to show you the scalable units, so you can see here the 50 U-racks. In between each one of the 52 racks with the 2 couplets in each are storage servers. So we have 16 object storage servers. This is actually the metadata rack here that has the metadata storage at the bottom of the rack. And then we have some LNet routers set into each of the rack, and of course future expansion capability and plenty of InfiniBand ports. I should mention that this file system is actually going into the location where Ranger used to be located in our data center. For those of you that visited our data center, we had these APC in-row coolers. Well, we're still using the APC in-row coolers to complement the cooling that's already available in the room and provide plenty of adequate cooling for the DDN hardware in the data center. So just a few more details on the hardware. So the 50U rack, I have to say, I had not planned on using 50U racks in the data center. Our data center was designed to handle 48 U-racks. And so these racks were about a ½ inch too tall to actually roll in the door. So we had fun tilting them over and getting them in the door, worked with the DDN engineers to get them in the door. But for those of you who are working on data centers, take it into account that you're going to have 50 U-racks coming very soon. Pretty tall racks. We had to feed each one of these with eight L630 circuits. So they're 30 amp circuits at 208. Each couplet, we're using 16 of the FDR ports as a direct attachment to the 16 OSS servers, so there's no switch in the middle, they're directly attached. The switches are only to connect up all the storage servers to make up the Lustre file system. We're using the SS8460 drive enclosures. These are the 84 slot drive enclosures, 10 per rack, 20 enclosures per scalable unit. And of course, these are the most dense, capable storage enclosures that you can purchase. And then, of course, all the drives are the 4 terabyte nearline SAS drives that are available now. Just to show you the logical layout, so this is the storage racks. These are all the OSS storage servers. They're all connected together on a FDR fabric. We then provide them out to our other production systems through both the LNet routers that have InfiniBand on them, FDR InfiniBand, and also 10 gig E currently, but capable of going to 40 gig E in the future. So we're trying to, again, plan for future expansion and capabilities. And again, we have both InfiniBand and gig E so that we can make it available to multiple of our systems at TACC. So again, the big thing for us is it hit more than the 20 petabyte usable capacity, and of course we've actually got more than 100 gigabytes a second of aggregate bandwidth available in the hardware. We've achieved at least 100 gigabytes, or more than 25 gigabytes a second per scalable unit, and are working on scaling out based on the LNet routers to drive it from Stampede and the other production systems. So. The design actually is set up so that we can bring in more additional LNet routers should we need additional capability to other systems or as we deploy new systems. In fact, we just announced a new visualization system that we're in the process of deploying this at the end of this year. And it's going to add additional 12 LNet routers to connect to Stockyard so they can access the file system from it. We're also planning, and this is something that we're still looking at and evaluating, but really we would love this to be the front-end cache to our tape archive system. Lustre 2.5 has introduced the notion of HSM in it. We plan to potentially leverage that moving into the future. And in fact, we really want to make this so that the users don't have to ever interact with a tape archive. We can just go ahead and use this as our spinning cache for the tape archive and have it handle all the tape recalls and everything for us. The other thing we're actually working on right now is metadata performance enhancement. We have deployed this now with active failover capability on the metadata servers. But of course, with Lustre 2.4, they introduced DDN, which allows us to use multiple metadata servers. We have not tested that as of yet. We've been just working on the initial deployment, and we plan to implement that as one of the next tests that we do before we put the system into production. And then another one is, of course, the network request scheduler. We're looking at the different policies here, particularly the client round robin over NIDs, so that we can handle better service and provide access to the files, even when the system's under contention and dominated by just a few jobs. We realize that it doesn't take many clients to be able to saturate the file system, and so we want to explore some of these different policy engines to potentially accommodate the users that are accessing the file system when it's under heavy load. So I do want to cover some of the numbers that we've achieved so far and the performance that we've met on the file system. 16 LNet routers. Right now we've configured them as direct clients, and this is just so that we can do initial testing of each of the scalable units. We've been doing a lot of effort to make sure that every one of the storage servers, every one of the OSTs is providing similar capabilities and performance. And what we did is we basically tested each one of the scalable units and measured the fact that they can push more than 25 gigabytes a second to each one of the scalable units. We then put 2 of the scalable units together with the same set of clients and achieved 50 gigabytes a second. Same thing when we went to 3 scalable units. But unfortunately, when we hit the 4th, we actually hit our client limit. We didn't have enough clients to really drive the system beyond the 75 gigabytes a second. So we're working now actually to test to get up to 100 gigabytes a second from Stampede clients. But again, we're going to need a few more LNet routers to actually be able to achieve that limit. But the interesting thing is with Lustre 2.4.1, we're actually achieving about 4.7 gigabytes a second from each client. Now this is a threaded write. A single write is doing about 750, almost 800 megabytes a second to the file system. This is actually substantially better than what we see with Lustre 2.15. If you're running a Lustre 2.15 client, you may have noticed that the performance on a per client basis is actually much less than this. In fact, we've typically measured about 500 megabytes a second from a Lustre 2.15 client to this file system for a single write, and then only peaking at a little over 2 gigabytes a second, so less than half of the peak capability with Lustre 2.15. We think we understand now that what change they made in 2.4.1 to meet that performance, and I'll mention that in a later slide. So I mentioned the 770 megabytes a second. This is actually a pretty big improvement. In fact, we've deployed the 2.4.1 client on our login and data mover nodes for Stampede so that we can actually achieve this type of performance. But again, when we use multi-threads, we were able to hit 4.7 gigabytes a second. The key is that they've increased the number of credits in 2.4.1 to 256. The default in 2.15 is 64 credits. For Lustre. So, but right now we're running the servers on Stampede are all set with 64, so we didn't want to change all the clients on Stampede to 256. So in terms of actually measuring this from Stampede, we mounted this file system on several thousand servers on Stampede as clients. In fact, I mentioned the 256 here. We achieved 65 gigabytes a second. Even scaling up to all 2,048 clients that I had it mounted on recently, we still sustain the 65 gigabytes a second. So that's our saturation point for the current Stampede clients. And right now we're really limited by the fact that we only have 16 LNet routers. We're going to have to scale up the LNet routers. But what's interesting is our performance testing with the LNet routers is there's almost a linear scalability as you add additional LNet routers. So if you have the capability on the server side, you can easily expand and scale out the capabilities on the client side by just adding in more LNet routers, which is how we wanted the system to be designed, so that we could control some of the bandwidth based on the number of LNet routers. So. I mentioned this before, but in Lustre 2.15, the number of credits set for the InfiniBand-based LNet is 64, and that's what we have set on the client nodes of Stampede. We did take one Stampede node and reconfigured it with the right setting, and we did see that it did get the expected boost up to about 750 megabytes a second on one single task, and up to 4 gigabytes a second for a threaded write. Of course, one of the big things we wanted to make sure of is that we had a very reliable file system. So we did experiment and test some of the failover capabilities as part of our deployment procedures. So this is kind of the procedure we followed. Basically, we identify all the OSTs that are on the pair. We initiate some DD processes to each of those OSTs. We make it pretty large just so that it does not finish before we begin the failover. We then shut down one of the servers. We record the individual process outputs as well as on the server and client sides, and we confirm and compare and confirm that all the recovery and operation of the failover pair with the 21 OSTs that are in the pair. And in this case, all the I/O completes within 2 minutes of the failover. So the good news is that we can sustain a loss of the server and maintain active reliability. Now, these failover tests are doing with manual failover. We're working on the automated failover still. Similarly for the MDS pair, we did the same sequence of interrupted I/O and collection on both the client and server side. What's interesting here is you can see the messages from you can see the primary metadata server here responding, and then of course once it fails over, the secondary metadata server at the other IP address available. So we're actually in the process right now of evaluating CorralSync and Pacemaker to automate the failover process. Again, we want to maintain high availability. We don't want to have a system administrator get involved to fix any of the I/O. Of course, this was all the artificial setup was done with manual shutdown, but we do plan to automate this process. So on the routed clients, one of the other things we wanted to make sure of is that we were getting good balance on all the clients. And again, this is something that we experimented with, and we did find that Lustre did have some limitations from our point of view in terms of handling of the clients. So Initially, when we mounted the file system on Stampede and we started running some of the tests, we did notice some uneven distribution of the requests coming into the routers. And it turned out that some of the clients thought that several of the routers were down. But we expected that the fact that when we had the system configured with the defaults, that would automatically note that when routers are down or up. But what we found is that it's actually important to have an additional LNet setting to check routers before use, so that it'll automatically update the router status. And this way, if a router goes down and comes back, it'll actually handle that in Lustre and automatically resume using the portal router should it go down. Again, this was something we didn't expect. It took us a little bit of testing and tinkering to determine that this was the culprit on that. But once we set this then all the clients now, if a router goes down, it automatically realizes it, and then when it comes back, it starts using it again. So, of course, this was a side effect of having the automatic router checks, but we do have clients encountering timeouts due to non-functional routers. So right now what we did to fix that is separate the router checks on router nodes. We added those additional so that we can make sure that all the routers are fully functional when we're performing the I/O to the system. So looking ahead on Stockyard, we actually are working to deploy this as a kind of our global workspace for all TACC resources. Right now we're in the process of deploying it on Stampede. We do plan to make it available on all the production systems. This means that we're going to have upwards of about 10,000 clients that are going to be mounting this file system. And some of them will be mounting it with direct attached or over InfiniBand through the LNet routers, and some of them will be mounting it over the 10 gig space. I mentioned this before, but we are evaluating the 2.5 version of Lustre for HSM functionality, and we plan to integrate this in with our tape archive ranch, which is currently a SAMFS-based file system. We do realize there's actually some work that we have to do to get it to cooperate with SAMFS. We are working on the quota management still. It's a little bit different in 2.4 from previous versions of Lustre, so be aware if you haven't upgraded yet, that's a little bit different. We're also working with DDN to set up the direct mon and integrated monitoring setup. We're looking at this as well as potentially monitoring and of course using the phone home so that they can be automatically notified of potential problems on the hardware. And of course we're doing a little bit of security evaluation on how we're going to make sure that the file system, we'll definitely mount it with no SUID and probably with root squash on all the production systems, just so that people can't in case something does happen and we do have a security incident, people won't be able to just delete all the files in the file system and destroy the user's data. So just in summary, this is something that storage is really something that we've had to keep up with. I have to admit, coming from the HPC side of the house, storage is always the secondary factor. It's always that other piece. But one of the things about all of our systems is it's also the weakest link in many cases. When we have interrupts on our production systems, they're almost always file system based. And it's either users doing bad things to the file system or something with the hardware. So we're very active in terms of monitoring, but it keeps growing at an exponential rate. In fact, it's even gotten faster than Moore's Law. We've been relying on Moore's Law for HPC for a long time, but now with the explosion of data, it's just becoming a race to keep up with the needs of our users. So, of course, high-performance file systems and reliable ones are critical for HPC productivity. It's something that, like I said, is probably the most frequent interrupt on all of our systems. And we want to make sure that the users are able to get their research and science done and not have to worry about file systems being down. And it definitely outweighs the system administration overhead. I have to say, the system administration overhead has gone way down as Lustre has improved. We do see that we're less and less having to deal with potential issues on the Lustre and software side of the house, and it's more if there's a hardware issue or something with one of the servers is not behaving properly or performing correctly. So, and of course, right now, in our opinion, the current best solution for cost, performance, and scalability is still a Lustre-based file system. We do run some GPFS at our site as well. However, with the open source nature of Lustre and the community behind Lustre and the wide adoption of it in the HPC space, we feel that it's the future moving forward. And with the additional features and capabilities that have been added into it recently, such as the distributed namespace, or D&E for metadata, distributed metadata, and also HSM, now it's becoming an enterprise class file system. And so we're really looking forward to the future of Lustre and moving forward. With that, happy to answer just a couple of questions, I think, if we have any questions before the next talk.